So pre-calc, welcome back. We're going to talk about Descartes' rule of signs with chapter 2, section 6. And basically what happened is somebody noticed a pattern. René Descartes is the person that noticed the pattern, so they named it after him. And what they noticed is the fundamental theorem of algebra still holds true if we consider imaginary zeros. So if you imagine for a second, and I know I've talked about this before, but if you shifted the graph up or down, or if you think about shifting the x-axis, because I can easily draw an x-axis for f of x, you can still see that the maximum number of zeros that it could have would be 3. And it's pretty obvious that right now it only has 1, but it could have 3. That indicates that we would have a cubic polynomial. So if I were to look at g of x, which is just down here, and again, it's easier for me to think about shifting the x-axis, but you can think about shifting the graph, because it's very obvious that this graph only has 2 zeros, but if we move the graph, it could potentially have 4 zeros, making that a quartic polynomial. Let me fix that cubic because it doesn't look like a C there. There we go. That's better. So what they're trying to get you to recognize then is that you can identify the total number of positive, negative, 0, and imaginary roots. So if you look at f, it's pretty clear that there's one negative root. And when I mean negative, I mean a negative 0. So if it's to the left of the x-axis, it's a negative. Are there any zeros to the right? Well, in this case, no. I'm only looking at this specific graph. When I say a 0 at 0, I'm talking about if it's exactly at the origin. But it's a cubic, and we know the fundamental theorem of algebra says that the number of zeros needs to add up, the multiplicities, need to add up to be 3. So what that means is that the multiplicities need to add up to be 3, but right now they only add up to be 1, so there must be 2 imaginary roots in this problem. And I know you're familiar with imaginary roots from Algebra 2. You can't say, I don't know what an imaginary root is. Maybe I should spend a quick second and remind you about how we write imaginary or complex numbers as a plus bi, and then also what's called the conjugate a minus bi. But we'll get more into that later. I guess right now it's just okay to recognize that there are imaginary numbers and we can get answers or solutions to be imaginary. So same thing with g of x. But this time, there is one root to the right of 0. There is one root to the left of 0. There's no root at the origin, so this one's still 0. But again, it needs to add up to be 4 roots, so there must be 2 imaginary. Reminding you on stating the left and right end behavior as x goes to negative infinity for f. It's going infinitely down. And then as x goes to the right, that function is going infinitely up. And then this one, again, I'm going to just keep this. This is unconventional to write plus or minus infinity, but I'll let you do this for g of x. As long as the end behavior is the same, I don't want to see 2 different answers over here. Other teachers might not allow you to do that. That's why I'm saying it's unconventional. So what kind of leading coefficient does that give us a clue for? Is, for f, left and down and right and up, that's your clue. And hopefully you have a good memory on this, that's your clue that that's going to be a positive leading coefficient. Whereas g of x, because they're both going infinitely down, you can see the graph, but I also have it written over here that will be a negative leading coefficient. So what is a guaranteed 0? I said this wrong. because we know the 0 is x equals -4 up here. So we want to write the factor, which remember that factor is the opposite, so x plus 4. Whereas on g of x, x plus 3 and x minus 3 for your factors. Please let me know if you're confused on the factors. We write the opposite for factors for the zeros. For each of these, because it's a polynomial, the domain is all reals. Now the difference is for odd functions, the range is all reals as well. But with an even function, like g of x is, it's going infinitely down, but then stops once we get up to 5. So -infinity to 5. And please don't forget to pause the video at any point. Make sure you re-watch it if you need it. Take notes, and I'm going to move on to the next page. Again, don't be afraid to try things on your own as well. But this one's a definition, so you might want to just wait until I give you the definition. So I believe you've learned the fundamental theorem of algebra before. The only thing is you might not have known it was called this. But basically what it boils down to is an nth degree polynomial. I don't know what's going on. There we go. An nth degree polynomial has exactly n number of roots. So if we're talking about a third degree polynomial, it has 3 roots. Now all 3 roots could be the same, just so you know. A fourth degree polynomial has exactly 4 roots, 4 zeros, 4 x-intercepts. Well, I shouldn't say x-intercepts because sometimes they're imaginary, and we never write imaginary numbers don't go on the x-axis. So roots of the polynomial can be positive, they can be negative, they can happen at 0, or they could be imaginary. And he wrote "and" in here because there could be a combination of all of these. But at that point, it better be a 5th degree polynomial. I'll get a little bit more into that soon. Now, Descartes came up with these rule of signs, which is kind of interesting, and it's sort of difficult to follow. But it's a good indicator on how many roots there are it's a method, let's put it that way, to find the possible numbers, possible number of positive or negative, well, I should say and, because the method works for both. Possible number of negative roots. So as far as the definition goes, it's a lot more complicated than that. So what you are tasked to do is to look at a function and be able to count the number of sign changes. So maybe I should add that to my definition. By counting the sign changes. So before counting the sign changes, though, I need you to practice and make sure that you understand what happens when you do p of negative x. So if I ask you to do p of negative x, that means putting in a negative in for all of those x values. This is why we did this in Unit 1, because that's Unit 1 was like the lifeblood of everything that we do in pre-calculus. So just remember that if you take negative to an even power, it goes back to being positive. A negative to an odd power, though, stays negative. Negative to the even power, the sign stays the same there. Minus 2x plus 3. So what you do is you count the number of sign changes. I'm trying to color code this. Let's do blue with positive. So if I look at just p of x, right, that was a positive x. Let me just write out as if I said it. This is going to be your method to figure out the positive number of possible roots. So you see how it goes from a positive to a positive? Oh, it finally changes. I'll write p instead of minuses and pluses. So a positive to a positive to a negative to a positive to a positive. So it changes signs here and it changes sign here. So there were 2 sign changes. Right. And what the Descartes rule of signs says then is that there's either 2 or 0. And the reason why there's 2 or 0 is if you think about, like, if we have a root that's positive and we want to keep the same end behavior, it would have to cross the axis twice. So they go down counting by 2s. So we always skip a number and then go to the next one until we reach 0. Possible positive roots. Now, I don't expect you to get it right now. We're going to practice this, obviously. So let me switch colors for the negative one, right? Right there we're looking at a negative x. So we look at the negative equation that we had, which went positive, negative, 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 positive. So what I'm seeing here is going from a positive to a negative switches. Okay, but then negative to negative does not switch, negative to negative does not switch, and then negative back to positive. There were 2 sign changes. So again, because we count down in skipping numbers, that means there are 2 or 0 possible negative roots. And this, I would encourage you to read this in a little bit more detail. Yeah, I've already answered these questions down here. 2 or 0. 2 or 0. And that's the thing, is sometimes the reason why it could be 2 or 0 is if it does cross the x-axis, it would have to cross a second time. But it might not cross the x-axis at all, which means it doesn't have to cross back. And it's all based off of the end behavior. If you were to look at 2x to the 4th, it has to have a positive leading coefficient, even degree. It has to end going up and to the left and up and to the right. So it might not cross the x-axis at all. But if it does, it has to cross a second time. Either it's negative or positive. Again, I'm going to talk more about this. You just have to wait till the next video. But before doing this some more, we have to learn a few other things.